This is the real-time impedance measurement unit for spring 2021 of USF's capstone design course in electrical engineering, featuring Mike Laing, Tyler Lillo, Arlene Roberts, and Jason Welton.
For our IMU project, our biggest motivation came from Dr. Fan. She has been recently working on and researching a lot about harmonic injections, and when we reached out to her to be our faculty advisor for the project, she came back with an idea to create an IMU device that uses these same harmonic injections over a wide variety range of frequencies. Some information about the project is that using voltage and current harmonic injection to measure impedance dynamics has been proven in theory and laboratory simulation, but complete hardware implementation of an affordable device specific to this purpose has yet to be fully realized. Such a device would be very attractive for practical application of the proven technique. The IMU is a low-cost, compact, portable, and self-contained device that can be used to measure terminal current and voltage as a harmonic injection is administered. The IMU then processes the measurements into a linear impedance curve across the injected frequency range and stores/displays the data for the user. The device does this efficiently without external power. The IMU provides the user with the flexibility to perform impedance analysis in a variety of settings without the necessity of cumbersome and expensive equipment. The biggest risk that we ran into from the beginning of the project to the end of the project is that we did not pull requirements for the test condition restraints. We initially wanted to test the device in a different condition than what we were provided at the end. And to get around this, we slowly adapted our device for these new testing conditions. And how we divided our work amongst ourselves is that Arlene mainly did the GUI software development, Jason did the software and hardware testing with the hardware design and fabrication, Michael did the software development, and Tyler did the project documentations while also keeping us on track with deadlines and project scheduling. Thank you.
The IMU device is comprised of a Talon cell rechargeable battery with both 12-volt and 5-volt power buses. The physical peripherals of the device include a 13.3-inch portable monitor with a combined keyboard and mouse. A Raspberry Pi Model 3B interfaces with the physical peripherals and handles the digital user interface of the device. The Raspberry Pi also logs and displays the analyzed data. A TI board Launch XL-F28379D acts as the controller of the system, handling the ADC and FFT algorithm. The IMU device is capable of connecting to either a simulated network or a physical network. Physical networks are connected through a high-voltage oscilloscope probe and an AC-DC current clamp to acquire voltage and current measurements. These probes connect to the PCB where their outputs are scaled and given a DC bias that is sent to the TI controller ADC inputs. All components are encased in an aluminum case for portability. The IMU device is 17 by 13 by 6 inches, which is determined by our aluminum case. With the summation of all the component weights, we have confirmed that the IMU device is just under 14 pounds. With OSHA regulations having a maximum of 25 pounds, our device is compliant. The total power draw was calculated by taking the power draw of each component, which was calculated according to the power bus it is running off of, and we found the total power draw to be 32.7 watts with the summation of each component power draw. With the total power draw being calculated, we also needed to take a summation of the components using each power bus respectively in order to extrapolate the capacity for simultaneous power bus draw. The 12-volt power bus has a capacity of 53.2 watt-hour, and the 5-volt power bus has a capacity of 12.7 watt-hour. Taking the summation of both power bus capacities and dividing that by the total power draw of the IMU device, we confirmed the total runtime of the device to be 2 hours.
In Design 1, we started software development by building our first simulation in MathWorks Simulink. It was a single-phase RLC model, including voltage injection, along with a preliminary algorithm to process the voltage and current into impedance values. It was cumbersome and not compatible with MATLAB Coder, but it was a good first effort and proof of concept. As the project progressed, we built better models to develop the software package. Two key advances were the inclusion of buffer blocks to collect a sequence of samples that could be processed by the algorithm in batches. Additionally, the written MATLAB code was adapted to work within a Simulink MATLAB function block. The value there is that the function block is compatible with MATLAB Coder, which was used to convert the model to C++ for embedding on the TI board. The algorithm uses the FFT function to convert the time domain voltage and current signals into the frequency domain. The code then extracts the magnitude and phase values at the injection frequency. Finally, the impedance magnitude and phase is calculated and passed through the function output. This process repeats every second for a new injection frequency until 1 through 250 Hz has been analyzed. Testing of the algorithm model using various simulated RLC circuits yielded positive results with good curve matching. The results shown here use resistor values of 2 and 3 ohms. You can see system resonance where the phase angle crosses 0 and the magnitude is around 6 and 9 dB. At this stage, the model was ready for measurement and communication systems to be added. The final version of the model utilized the specialized Simulink library of blocks for the TI family of C2000 processors. These included the hardware and communication settings for the ADC inputs and the I2C connection to the Raspberry Pi. Memory read and write blocks were used to synchronize the output data. This model version shown here also contains a simulated voltage and current signal output through the DACs, which could be connected directly to the ADC inputs for testing of the firmware.
This is the current model that we will be demonstrating, as we do not have safe, reliable access to high-power systems. We will instead generate voltage and current measurements in line with a series RLC power circuit. The outputs from the DAC will perfectly mimic the expected outputs from the PCB. The PCB ordinarily would handle the signals generated by an oscilloscope probe and current clamp selected for this device. It scales their outputs and adds a DC bias to be compatible with the TI controller A-to-D converters. It was designed in Autodesk Eagle and built to order by Seed Studio. Parts were later soldered by hand according to IPC A610 and IPC J Standard Class 1 criteria. Now, let's fire up the device. We boot into a standard Raspbian operating system, which is a common open source fork of Linux. The demo program can be loaded and executed, where it will wait for the TI microcontroller. The I2C communication between the TI controller and the Pi kicks off the testing, and each second the buffers fill are evaluated and values are transmitted to the Pi for storage. As we have 250 frequencies to test, let's skip forward a bit. As the test completes, the log file is finalized and closed. The GNU plot software can then be run to generate the graphs we've all been waiting for, the impedance and admittance of a network over a whole frequency range. Thank you for watching our presentation, and feel free to ask us any questions you might have.